Yes. Now, is the PPT visible? And my speech is clarity is there, audible for all of you?
Yes, sir.
Okay, ma'am. Thank you. Okay. Now, this is the experiment list. At the beginning, we'll be analyzing certain switches. Those are static characteristics of SCR. SCR stands for Silicon Control Rectifier. This is basically one of the thyristor family member. We also analyze how the MOSFET switch works, what are their features, and IGBT features, track features. These four switches we study in the first three experiments. So SCR is a control rectifier switch. It's one of the member of the thyristor family. So when you say thyristor, it is a 4-layer, 3-junction semiconductor switches. MOSFET stands for metal oxide semiconductor field effect transistor. It is a family under BJT, bipolar junction transistor. That's a transistor family member. IGBT, insulated gate bipolar transistor. So these two switches coming under the transistor family. So they are 3-layer, 2-junction switches. Then track. Track is a member under thyristor family. Okay. So track and SCR coming under the thyristor family. So they are suitable for the high power applications. Track is also a 4-layer 3-junction switch, but a track is nothing but two SCRs connected in anti-parallel. Track is a switch we use in the fan regulators. In the fan regulator, very common element available is a track. So which conducts power, it conducts the current to flow in both the direction. So one best example is fan regulators. Very common example, fan regulators. And SCR is used for the lighting applications, AC drive applications, so many applications SCRs are used. Lighting, you say you take a cricket stadium, floodlights will be there. They want to control the illumination. And then maglavs, trains, they use SCRs in AC drives, and even also in DC drives when they use for converting AC to DC and all. And MOSFET IGBT is very commonly used in all inverter circuits, UPS. You take any electronic gadgets, we convert AC to DC and then DC to DC, DC to AC, so many conversions will be there. Preferably in the inverter circuits, DC to AC conversions, MOSFET IGBTs are used. They are suitable for the high switching operations. So one thing you should understand that in the entire power electronics, what are the switches we use? Those switches will be operating in the either cutoff region or you say not active region, you say saturation region. Saturation means it will be completely turned on. Cutoff means it will be completely turned off. We never use these switches or semiconductor devices as an amplifier here. We use all of them as a switch, solid state switch to open and close, nothing else. We can open and close the switch at very, very high frequency or maybe at moderate 50 Hz supply frequency also. So these are the devices we make use and do the experiments in henceforth. And we have the experiments like SCR turn on circuit using synchronized UJT relaxation oscillator. So this is one more switch called unijunctional transistor. You say you have heard about BJT, bipolar junction transistor, but this is a UJT, unipolar junction transistor. So this has got vast applications, and this is used to generate the switching pulses for the SCR. One of the experiment we study. Experiment number 5 is SCR digital triggering circuit for a single phase control rectifier and AC voltage regulator. We know that when you say rectifier, it is a AC to DC converter. AC voltage regulator means AC to AC converter, like a fan regulator. Rectifiers used for charging the batteries DC drives, speed control of DC motor, we use the rectifiers, and even charging the batteries, all those things. In electroplating and all in chemical applications. AC voltage regulator is very common in the AC to AC applications, fan regulators, in maybe powertronic transformers like that. But we are handling digital triggering. When you say digital triggering, we generate the switching pulses to be given to the switches in the digital mode, like 1010. Suppose I keep 0000, my firing angle alpha is 0. I put 1111, my firing angle alpha is maximum 180. Like that I can vary the width of the switching pulses using digital triggering circuit. Experiment number 6 we handle with respect to the rectifier circuit, single phase controlled full wave rectifier with R and RL load, all those things. This is basically AC to DC converter. We take the voltage waveform, current waveform, we see how the DC voltage can be varied, all the stuff. Then experiment number 7 is AC voltage controller using triac combination. So you should know one should know the abbreviation for triac. Triac is basically triode, TRIODE, triode that works on AC signal. Okay, that's a triac. And diac means diode that works on AC. These are the switches we use normally in the fan regulator. Okay, triac and diac we use in the fan regulators. So this circuit related to the AC to AC conversions. We do all type of conversions in every experiment, different type of conversions. So one among them. So this is related to all your switching characteristics and some converters. We are going to use it here till 7 experiment. Remaining experiment, you can see everything speed control. These are very interesting. We can do the speed control of a DC motor, speed control of stepper motor, speed control of universal motor, speed control of separated DC motor, and also we study about the inverters. These are the applications of the powertronic converters. One of the applications of powertronic converter is speed control. So these are the list of the 12 experiments. This covers the entire 5 modules. So I'm not here to explain every experiment and mess it up. I'm not going to do that. So we'll be discussing only 2 experiments. Experiment number 1, experiment number 2. That is how we are going to conduct these 2 experiments. We are going to understand today. So very important thing is once you come to the lab, we'll share the complete manual today itself by today evening. Myself and Champa ma'am will be there in the lab for all 3 sessions. Any doubts, you can talk to us. Any problem with the labs, conduction, and all those things, we always discuss with us. Of course, I have converted my EMFT group to PE lab group so that all the students are there in that. So henceforth, we can communicate through that group called PE lab. Right? So before going to start your switches, experiment 1 and 2, I would like to share some information about the powertronic converter. Then we understand how we do analyze this characteristics of the SCR and the MOSFET and IGBT. So when you say the very what is a buzzing word, power electronics, everywhere power electronics is there. First of all, what is power electronics? So how you define power electronics? So basically when you say power electronics, it deals with the control and conversion of electrical power. So power electronics we use to control and conversion or convert electrical power from one form to another form using solid state switches, okay, or a semiconductor switches. So power electronics are used to converters, a power electronic system or power electronic converters are used to control or convert the electrical power from one form to another form. What's the one form to another form? It may be AC form or DC form or vice versa. Okay, using solid state switches. So when you say the word system, so we say solar system, okay, some file system, okay, operating systems. When you say system, so essentially system will be having the set of what you say synonymous or you say equivalent or you also you can say similar components. Similar component, their characteristics remains one and the same more or less. It has got set of components. When you say system, solar system, Sun is the head of the family, and all planets are the members of the solar system. All of them are planets, and Sun is a star. The Sun is holding everybody, head of the family, and all the planets will be coming under same category. They are called planets. So there's equivalent objects, similar objects. Similarly, when you say Polytronic system, it has got both electrical electronic stuff and load, all of them coming under electrical electronics engineering only. It has essentially has got three important parts. So one is power processor or a Polytronic converter. Polytronic converter. Okay, like we have a rectifier, inverter, chopper, AC voltage controller. Those are the Polytronic converters. And second part is a load. Load is very essential because the load can be an induction motor, it can be a DC motor, it can be a oven, it can be a refrigerator, it can be anything, any electronic. It may be aviation system, it can be medical electronics, any load it can be. So we definitely sense some parameters of the output side. Sometimes input parameter also will sense. And a reference signal will be given by the user. User will tell that I want a speed at 1500 RPM is my speed requirement. So do whatever you want. I want 1500 RPM. That's what the user will give the reference. Based on the reference and the sensor signal, I may sense the speed, I may sense the temperature, I may sense the voltage, I may sense the current, I may sense any parameter, I may say pressure also. Some parameter I sense I give to the controller, and user will give his own input data. So based on the comparisons of the sensor data and the reference data, we can give the control signal to the power processor or Polytronic converter to fine tune the output. The output may be speed or torque or the voltage or the control of the load, right? So these things can be controlled using your Polytronic system. And the power input is maybe we say input voltage VI, input current II. So the power input may be AC or DC. Power output may be again AC or DC. Right. So it depends what type of load you are going to use. So you keep it in mind that Polytronics essentially deal with the control and conversion of electrical power from one form to another form using solid state or a semiconductor switches. And it has got essentially three parts. One is power processor or Polytronic converter, load and controller. Controller, the input is reference signal or user defined signal, user required data. And another input is sensor signal. Sensor signal can be any physical parameter. It can be analog signal or a digital signal if my controller itself is digital in nature. Because controller, you talk about controller here, there are different type of controllers. We may handle or we may rig up the controller using analog circuits, analog electronic circuits. You have studied already AEC. Analog electronic circuit like a MOSFET, BJT, IGBT switches I'll use some, maybe in some other mode. Or we can design the controller using digital electronic circuits also, using ICs. We have studied these two subjects last time. Using this, we can rig up the control circuit. If you still go for advanced mode, we may have a controller using microcontroller or a microprocessor, or we may have a DSP, digital signal processing is one type of a controller, or you may have a still advanced FPGA, field programmable gate array is one more controller. Likewise, we can design controller of any kind depending upon the load we are going to handle and the system we are going to handle. When I say digital Polytronic converter, everything will be digital in nature like that. These are the fundamentals. When you say Polytronic converters, we have the three types essentially. One is DC to DC converter. Choppers is used for charging batteries or control speed control of DC motors, and you want to step up the voltage, step down the voltage in the laptops and all. Rectifiers converts AC to DC. So this is again used in the charging battery, DC drives, so many applications. Inverter is a part of the UPS, DC to AC. AC voltage controller, I think one of the demonstrations we have seen in the workshop last class. That is the AC voltage controller, where we have seen two thyristor and anti-parallel. So these are the type of converters. Now, when you see the Polytronic converter components, semiconductor switches, basically the first one, semiconductor switches, there are three family members. Diode family members. Under diode, there are different type of diodes are there. General purpose diode, Schottky diode, high frequency diodes, and varactor diode. So many diodes are there. So diode is essentially having two layers and one junction diode, anode and cathode. We are aware of this. So this is a one kind of family member, one type of family. When you go for a transistor, it's a 3 layers, PNP or NPN, correct? Maybe collector, emitter, base. This may be collector, this may be emitter, this is a base. It's essentially 3-layer, 2-junction device. When you go for a thyristor family member, it has got 4 layers and 3 junction J1, J2, J3. Even it has got anode, cathode, similar to diode, and but one control terminal called gate. Gate is a control terminal. In the BJT, base is a control terminal, right? So even in the thyristor or a SCR, the control terminal is gate, and the power terminals are anode and cathode. Now, when you go for the other components of the power electronic converters, we have a energy storage elements like inductor, capacitor we use. Other components we measure transformer, control circuit, all the stuff. So these are the parts of the power electronic system. Okay, it may be semiconductor switches in the power processor, energy storing elements like maybe in the load or some control part. Other component transformers we use for stepping up, stepping down purposes, isolation purposes we use control circuits to give the pulses to the switches. So this slide, I'm not going to go in depth, but I'll give a brief idea how the switches are classified. I told you we'll be studying SCR, MOSFET, IGBT, and TRIAC. These are the 4 switches we are going to analyze and see their characteristics. So how the switches are classified here, where the switches fit in the classification, we see. There are 4 types of classification. First one is based on controllability. Based on controllability. Controllability means it can be controlled, semi-controlled, or uncontrolled. How the switch is. Basically, diode is an uncontrolled switch. It doesn't have any gate terminal or a base terminal. When you take a switch, your diode, it will just turn on. That's all in one direction. It's a unidirectional switch. When anode is positive with respect to cathode, once the voltage is a little bit more than the threshold voltage, maybe 0.8, more than 0.8, it will conduct, right? So suddenly you give the voltage, it will conduct, that's all. In the reverse direction, it won't conduct. Okay, it is unidirectional switch, but it's uncontrolled. I don't have any control on it. Just give the supply, it will turn on in one direction. But when you go for a semi-controlled switch, like SCR and TRIAC, the semi-controlled means we can turn on the SCR, but we cannot turn it off. We cannot turn it off. Only our work is we can turn on them. We cannot turn it off. For that, we have to completely turn off the supply, or we have to completely turn off the current flowing to the switch, like that. Fully controlled switch. We have a BJT, MOSFET, GTO, IGBT. When you say fully controlled, you give the base drive, the switch will turn on. Remove the base drive, switch will turn off. Same thing holds good for a MOSFET, IGBT, GTO and all. Give the base drive, it will turn on. Remove the base drive, it will turn off, like that. So these are the categories coming under the controllability, based on the controllability. Remaining 3 types, these are not the time to discuss. Maybe in the 3rd or 4th instruction class, I'm going to discuss about it. But time being, keep it in mind that based on controllability, we have a power diode uncontrolled switch. Semi-controlled switch means SCR and the TRIAC. We can turn on, we cannot turn off. For that, we require auxiliary elements to turn it off. Fully controlled switch, we can fully turn on, fully turn off, depending upon our requirement. Give the base drive, it will turn on. Don't give the base drive, it will turn off. So I'll give one small example here. Let us go to the screen. So suppose I take a transistor. I'm using transistor as a switch here, collector, emitter, base. I put some base current limiting element. So I want to connect a bulb here. One bulb. Then I have a supply. Supply is 230 volt DC. So this bulb also 230 volts bulb. So here we have 2 loops. This loop we say loop number 1 is a control loop. Control loop. And this loop number 2, we say power loop. Power loop, where more current flows. Left hand side we hand with only 5 volts, that's all, not more than that, 5 or 3 volts. The moment you give the 5 volt, the moment you give the base drive, the collector emitter is shorted, switch will be closed, so that huge power flows from the source to the bulb through the switch like this. In this manner, bulb will glow. The moment you remove the supply here, 5 volts, you remove the 5 volt supply or open the switch here. You suppose you have a switch here, open the switch here, bulb will turn off because the BJT will go to off mode, cut off region. It will go to off state so that power won't flow to the bulb will be turned off. You can see here we can control 230 volts by using a very small 5 volt. Small 5 volt. Even you take a television, you have a remote, so you give a small infrared signal to the TV's receiver. It receives and closes the relay. So you may have a 1.5 volt battery, 3 volt battery is there in your remote sensor, right? 3 volt is sufficient. You just give some infrared ray signal that is censored by the receiver available inside the TV. It will close the relay, so TV will be turned on. A small voltage is sufficient to trigger the switch so that the power loop will be turned on, so that huge current flows to your bulb or your TV. So the bulb maybe bulb or TV also, one and the same, no problem. So this we say fully controlled. Fully controlled means you give the 5 volts, switch will be turned on. Remove the 5 volt, it will be turned off. So that's the analysis one should do. Okay, these are the fundamental things. So what and all we have learned here, the basic things we have learned here is, we have learned that as per the experiment list is concerned, we are going to analyze the 4 switches, SCR, MOSFET, IGBT track. SCR track is coming under thyristor family member, MOSFET, IGBT coming under transistor family member. Then we have seen there are some controllers, converter circuits like AC to AC, AC to DC, DC to AC converter circuits are there in the list, and also AC to AC. All the 4 type of converters we handle. Then we have a speed control application of power and converter, speed control of DC motor, AC motor, universal motor, stepper motor, all those things we do here. So this is the list you should know. Then we have understood what is power electronic system. Essentially has got 3 parts: power processor, a power electronic converter, load and the controller. And we came to know there are 4 types of power electronic converters. Then what are these power electronic converters consists of? Basically, maybe you have a switching family members like your diode family members, 2-layer 1 junction, transistor family member, 3-layer 2 junction, thyristor family member, 4-layer 3 junction, energy storing element, other components. These things we have learned. We also learned what you mean by uncontrolled switch and semi-controlled switch and fully controlled switch. Uncontrolled switch means we don't have any control. Give the voltage to that, it will turn on. Semi-controlled switch we can turn on, but we cannot turn off. Fully controlled, we can turn on, turn off. It's in our control. That's what we have learned. Okay. So far, if you have any doubts, you please let me know. Now we'll go to the experiment. The first experiment is static characteristics of SCR. Note down all of you. SCR stands for silicon controlled rectifier. I'll be telling so many information. You better take your pen, book, and note down. Okay. So some of the information may not be there in your manual also. Silicon controlled.
Yes. Show the previous slide.
Yes, ma.
Can you please show the previous slide again, sir?
Please. Yes, ma. Yes. Any doubt you have?
No, sir. You can proceed now.
You want to note down something here?
Yes, sir. I took it.
You took it. Okay. Okay. Shall I go to the next slide?
Yes, sir.
Note down that SCR means silicon control rectifier. It is coming under thyristor family. So it is a thyristor family member. It's basically a thyristor family member. And the thyristor you are going to study in your theory also. So many family members. One is SCR. Then you have a triac, diac. We have RCT, reverse conducting thyristor, MCT, mass control thyristor. Many are there. So one among them is SCR. SCR is one of the family member under thyristor. So thyristor is the name of the family. Under that, SCR is a silicon control rectifier. We use the SCR as a switch here. Very simple. We never use SCR for amplification and all. So in entire power electronics, we use the semiconductor family as a switches. Okay, not as amplifier. That you please note down. Now, what's the objective of this experiment number 1 is that to show that forward breakover voltage VB0 of the SCR decreases with increase in gate current. This is one of the objective. To show that forward breakover voltage VB0 of the SCR decreases with increase in gate current. So let us see what is that, what's the meaning of that later. Next, we are going to measure holding current, latching current of the given SCR. We are going to measure the holding current and latching current of the given SCR. And third, we are going to study the static or forward characteristics of the SCR, given SCR. We want to know the static or forward characteristics of the SCR. You might have written the forward characteristics, or to say input characteristics, output characteristics of a transistor. Okay, common emitter mode, we have input characteristics, output characteristics, like that. Same thing, we are going to do the same thing in the for SCR also. So objective is to show that forward breakover voltage of the SCR decreases with increase in gate current. We are going to measure the holding and latching current of the SCR to study the static characteristics of the given SCR. These are the three objectives. Again, still before going to do the experiment, we should understand how was the symbol of the SCR and what are the features of the SCR. So when you see the SCR, the symbol is SCR is similar to a diode. We write a diode like this, but it has got a control terminal called gate terminal. Extra element is terminal is gate terminal. Anode terminal, cathode terminal, similar to your diode. Apart from that, we have control terminal called gate terminal. That's why this is a control terminal, semi-control terminal, but it's a control terminal. This how the thyristor looks like, SCR looks like in the market. You can see here, one may be a anode, one may be cathode. The small terminal is a gate terminal. This is how it looks like. The area of this switch is large compared to the transistor because it can handle huge current, huge voltage it can withstand without any problem. So that is why the SCRs are used for huge power applications. When you see the SCR, as I told you already, it's a 4-layer 3 junction. Junction 1, junction 2, junction 3. It has got 3 terminals, anode, cathode and the gate. So one SCR is equivalent to 2 transistors connected in this manner. So maybe suppose I take a knife and cut it like this. Cut it like this. So I get a PNP here and NPN on the other side. That's what is broken here, which means that essentially the SCR is essentially your 2 transistors connected. One is PNP, one is NPN. That's what the circuit also shown here. So SCR is equivalent to 2 transistor connected in this manner. So we have a derivation in your theory, 2 transistor model of SCR. For that we are going to relate anode current and the gate current and all. Okay. But you should understand that your anode is a power terminal through which the huge current flows. Gate is a control terminal and cathode is a common terminal, common between the input and output, or common between the power loop and the control loop. Gate is a common terminal. So always ensure anode is a power terminal. So when I say anode current, huge anode current flows because I have a load here, some supply with the cathode, anode and cathode. This is my power loop, and control loop is gate. Take the wire from the gate and give some small voltage of 5 volt. Cathode is common between the control loop and power loop. Cathode is common, right? Through anode, huge anode current flows here. That is a power terminal, and gate is essentially your control terminal. You can see 2 loops here. Left hand side loop is the control loop. You give 5 volt, SCR turns on. Anode and cathode is dead short, so that it works like a switch, right? The same circuit, if you get switch and the source is something like a switch like this. The switch is nothing but SCR. Close the switch by giving gate terminal, it flows forever, then the current start flowing, that's the anode current, start flowing. Right, we don't have option to turn off. If at all you want to turn off, your anode current should be less than the certain value of the current. So those currents we see later, what are those currents stands for. Now when you take SCR, there are 3 modes of operation of SCR. One you say forward blocking mode. What do you mean forward blocking mode? When anode is positive with respect to cathode. So junction 1, junction 2, junction 3. Junction 1 and junction 3 will be forward biased because P and PN will be forward biased. Junction 2 has got the layers N and P will become reverse biased. So in the forward blocking mode, junction 1, junction 3 are forward biased. Junction 2 is reverse biased in the forward blocking mode. So current won't flow. But still, you see the plot here. What the plot here? Plot is nothing but the voltage VAK versus the anode current IA. VAK is the voltage from anode to cathode versus the anode current. In the forward blocking mode, you observe the SCR won't conduct because of blocking mode, forward blocking mode. Small leakage current will be flowing here. You can see small leakage current. That value of the leakage current will be in microamps. In spite of the small leakage current will be flowing, that's in microamps, but that never turn on the load. The moment you give the gate signal, we can come from forward blocking mode to forward conduction mode. Okay, avalanche breakdown takes place at the junction 2 so that SCR turns on. In forward conduction mode, SCR will be in on state. When the SCR conducts, the voltage from anode to cathode will be very, very small because it works like a switch. It's shorted, very, very small. You can see immediately from the VB0, what you call forward breakover voltage, because I keep on increasing VAK, it is not conducting. At one particular point, it breaks here. So it breaks under such a way that the voltage across the SCR will be less than 1 volt. We'll come to this particular point. So thereafter, if you increase the current value, current will increase, but voltage won't increase much. Slightly voltage will increase. You see the slope. Voltage will slightly increase, maybe from 0.8 to 1.2 volt. That's all. The drop across the switch will be 0.8 to 1.2 volt. Of course, remaining supply voltage of 230 will be across the load because this switch is this SCR is working like a switch, right? Now, again it depends. Without gate signal, we can turn on. Gate signal need not be. I keep on increasing the voltage. What you call the forward voltage. If forward voltage is more than certain value, SCR turns on. But that is very hazardous, very dangerous. It may damage sometimes. That is not the better method of turning on SCR. There are different methods of turning on SCR. One method is increasing the forward breakover voltage. Increase the voltage more than the forward breakover voltage, what you call VB0. If you go more than that, it will conduct, it will turn on. But it's not a healthy condition. It's not a healthy condition. Your work is to turn on the SCR by always giving the gate current. So gate current, suppose I put the gate current IG1. Maybe say IG1 is some 10 milliamps. The moment you increase the voltage more than this particular value, the switch conducts, it will move from the maybe some higher voltage to very low voltage. It start conducting, thereafter current will increase, voltage won't increase across the switch. Then I may increase the gate current a little bit more, IG2 some 20 milliamps. So IG2 is more than IG1. IG2 is more than IG1. So in that case, what will happen here? You can see here within a small breakover voltage also, SCR will be turned on. I'll show you the difference here. So this VB0 maybe say 30 volts. This may be 25 volt. So this may be 20 volt. This may be 19 or 15 volt. When you increase the gate current, SCR conducts very faster. Okay, XCR conducts very faster. So here actually the relation is not given properly. In fact, here IG3 is more than IG greater than IG2 greater than IG1. There's some error in the printout. But IG3, when the gate current is very huge, it'll turn on within 15 volt. My forward breakover voltage VB0 is only 15 volt. Within 15 volt, it can turn on. So the 15 volt is fall to less than 1 volt. So thereafter, we can increase the current by increasing the load. So what I'm saying here is the two things. One is you can turn on the SCR by increasing the voltage without giving gate signal also. It will turn on, but it's very hazardous, not a healthy condition. Second method is by giving a gate signal. We have to give the gate current. So when you give the gate current, SCR will turn on comfortably. Like we give the base current to the transistor to turn on. Same thing, you give the gate current to the transistor to turn on. It will turn on comfortably. If the gate current is more, if you give the huge gate current, it will turn on very faster. So within 15 volt, it will go to 1 volt and the current will keep increasing thereafter. Right. So that is a forward conduction mode. When you say reverse blocking mode, my anode is negative with respect to cathode, then junction J1, J2, J3 among them, junction J1 and J3 will be reverse biased. Only J2 is forward biased. Right? Because you see the layer, what are the various layers? Because my cathode is positive, anode is negative. So junction J1 and J3 are reverse biased. And junction J2 is forward biased. Okay, forward biased. So in this scenario, the SCR will never turn on. It will never turn on in the reverse blocking mode, which means that SCR will not conduct in the reverse direction. It's a unidirectional switch. In the sense, unidirectional control switch. Current will flow from anode to cathode. We cannot make the current to flow from cathode to anode. If at all you want to make the current to flow from cathode to anode, there's one more breakdown, reverse breakdown voltage. You should apply reverse breakdown voltage of very high value. It will break. Current will flow abruptly, immediately from cathode to anode, but it will damage. It's a permanent damage to the switch. So that is all about the forward blocking voltage, VB0, reverse blocking voltage, VBR. All of them are very, very important. What the switch we use in the lab is called, as you can note down, TYN616 is the SCR family number. TYN616 is the switch we use here in the lab. So TYN616, TYN is basically the serial number or a code. 616 means we can say 616 is 600 plus 16. So it's capable of handling 600 volt, 16 amperes of current. The 600 volt is basically a forward blocking voltage. Forward blocking voltage. If you give more than 600 volt, then SCR will conduct without gate signal, but it may damage the part of the SCR. That is not healthy. Or otherwise, it can withstand 600 volt without turning on. That's very important. That is a forward blocking voltage. Forward blocking voltage is 600 volt. And its current rating, it can handle up to 16 amperes. It's a small switch, but it can handle 16 amperes. That's the meaning of the 616. All of you note down. TYN 616. 616 is nothing but 600 plus 16. It can handle 600 volt. Well, 600 volt is nothing but forward breakover voltage or a forward blocking voltage from anode to cathode. 16 amps is the anode current that is flowing here. Okay, that is flowing, that anode current, basically anode current, what you are saying here. Any doubts you have here before me explaining this experiment, the loops and all? If you have any doubts, you please let me know. Do you have any doubts here? What and all are told so far? I'm talking about that. Now you see the experiment here. We want to plot the static characteristics of the SCR. It's a plot of IA, anode current, versus VAK. VAK is the voltage between the anode and cathode of the SCR. We want to plot it. And we want to see how the plots look like. The plot will be getting something like this. Okay, voltage will be keep increasing. At one particular point, voltage will fast to 1 volt, less than 1 volt. Thereafter, current will be increasing, so that we can increase the current by loading the power loop. Now, let us understand there are two loops here also. This is your control loop. This is your power loop. This is a power loop. Power loop means the huge current will flow. This is a control loop where we give small voltage to turn on the SCR, like I already told you. Because my gate is a control terminal. When I give the small voltage to the gate and the cathode, SCR turns on. What do you mean by SCR turns on? Anode and cathode is dead short. When the anode gets dead short, the huge current will be flowing in this loop for the load. Here my load is 25 ohms, 6 amps rheostat. It's a load here. 25 ohms, 6 amps. You can also put bulb also, but here we are using a 25 ohms, 6 amps rheostat, which is in cut-in mode, fully cut-in mode. Okay, that is the power loop on the right hand side. Left hand side, you have a control loop here. The control loop, basically when you say control loop, we give a small voltage for SCR to turn. But since we cannot go for a 300 volt DC or a 600 volt DC, they are very hazardous, right? In the lab, we conduct experiment only with 30 volts. So you won't get shocked wherever you touch, whatever the part of the circuit you just handle, you touch them, nothing will happen, because the human being sense the shocking from 60 volt onwards, not below that. Okay, that's not high voltage, but as far as photon is concerned, or any electronic gadgets, 60 volt onward, you feel shocking sensation. So we have restrict to 30 volt and 15 volt here, not more than that. Okay, now let me explain what various elements are available here. We have taken here two power supplies, PS1 30 volts 5 amps, PS2 15 volt 500 milliamps. These are the two power supplies. We take two ammeter. One ammeter will be the gate current IG. This ammeter will show the anode current IA. And this is a voltmeter which will show VAK, voltage across the switch, potential difference across the switch. These are the two potential divider. For the proper turning on the switch, we have a two potential divider to divide the voltage and then fed to the SCR. And on the power loop, we have the rheostat as a load, 5 amps fuse for the protection, switch 1 and switch 2 to close and open the power loop or the control loop. These are the elements we have in the experiment. So one plus point is you need not to bring all the component one by one and rig it up. Everything will be there in the module. That's the main advantage in the power electronics lab. All our modules, okay. You have to bring the components one by one and rig it up in the spring board, all those things. No confusion of that kind. Everything will be there in the module. So different nodes will be there. You can connect them using a wires. Okay, you can connect them using wires. All these elements will be the part of the module. Okay, but this entire figure, it may not be the same figure in the module. On the module, we have a resistors one place, and then SCR one place, fuse one place. You have to connect them based on the circuit given. Right. Now let us see how this circuit works. Now the initial conditions of this experiment is, initial conditions, you please note down, all of you. Initial conditions. Initial condition number one. Initial condition number one is that power supply 1 PS1, power supply 2 PS2 should be made 0 volt. Okay, set the knob to 0 volt, and current knob, this is a voltage knob I'm talking about, PS1 PS2 voltage knob you make 0 volt, and current knob you put maximum current value. Rotate the knob to get the maximum, to extract the maximum current from the power supply. Initial setting is in both PS1 PS2, voltage knob should be minimum or 0, current knob should be maximum to draw the current required from the power supplies. The first initial condition. Second initial condition is that switches S1 and S2 will be open. S1, S2 both should be open. Second initial condition. Third initial condition that rheostat should be in cut-in position. Rheostat should be in cut-in. When you say cut-in, entire resistance is included. You please note down. Rheostat cut-in means entire 25 ohms is included. Cut-in. Cut-out means excluded, which means that I will be getting only 0 ohms, which is dead short. You are not supposed to cut out the rheostat. It will short the supply itself. So these are the three initial conditions one will follow. First initial condition, PS1, PS2 settings are that voltage knob should be minimum, current knob should be maximum. Setting 2, both switches S1, S2 will be in open mode or a off state. And setting 3, rheostat should be in cut-in position. So before turning on the supply, you rigged up the circuit, but S1, S2 should be open, rheostat should be cut in, power supply 1 and power supply 2, voltage should be minimum, current should be maximum. These are the initial conditions you have to follow. Okay. Having set the initial conditions, let us see how to conduct the experiment. Okay. Now we set here S1, S2 is off only. On the procedure, initially what we do, set PS1 to 30 volts. PS1 to 30 volts. And the PS2 is in 0 only. Close the switch S1. When you close the switch S1, 30 volts will be available across the switch. Same 30 volt will be visible in the voltmeter, that is VAK voltmeter. Same 30 volt will be available because switch is open here. I am not giving any gate signal. When switch is open, plus to the your anode and minus to the cathode point where a voltmeter is connected, it will show exact 30 volts. So voltage across the switch is 30 volt means the switch is open. It's not conducting. Right? Then there's the first thing you have to do. Set your PS1 30 volt, close the switch S1, same 30 volt will be available. Then the close switch S2, gradually increase this PS2 from 0 to 1 volt, 2 volt, 3 volt like that. That time gate current will flow here. It will be start increasing. Gate current will be starting from 1 milliamps, 2 milliamps, 5 milliamps like that. Okay. At one particular point, somewhere around 6 to 7 milliamps of gate current, suddenly SCR start conducting. It will turn on. Suddenly SCR turns on, which means that we require 7 milliamps of gate current to turn on the SCR. And you will come to know what's the gate voltage from the supply we have seen here, maybe some 4 or 5 volt. Then what's the gate current is 7 milliamps we come to know. Then SCR turns on. Once SCR turns on, voltage drop across the SCR will fall less than 1 volt. Maybe 0.8 volt like that. Less than 1 volt will fall suddenly. Okay. So which means that SCR is turned on. When the SCR turns on, suddenly huge current flows in the circuit, maybe some 0.6 ohms, 0.6 amps or 0.8 amps. Suddenly current shoot up from 0 to 0.6 amps because SCR is turned on. So 0.6 amps of current is flowing in the circuit. This is the first reading. What are the readings? You have to note down what is gate current 1, IG1, that's 7 milliamps at which SCR is turned on. So you can see here the voltage drop across your VAK. When you keep increasing gate current, the VAK will be slightly reducing, maybe 30 to 29.9, 29.8, 29.5, suddenly to less than 1 volt. This 29.8 is what you say forward breakover voltage, VB0. So up to 29.8 was withstanding. From 29.8 suddenly rushed down to lesser value, that's less than 1 volt, 0.8 volt. It has gone down. So this 29.8 volt you have to note down here. So this is my gate current. I told you 7 milliamps. I'm going to show the tabular column also because what we do I want to note down here. 7 milliamps exactly. The SCR is turned on. The respective VB01, what we got is some 29.5 volts. Whatever we got it, we have to note down. Then VAK falls to 0.8 volts. Current will be 0.6 amps. Okay, the first reading we take. So at the beginning, the voltage drop across the switch is 30 volt. When you keep increasing the gate current in the control loop using a power supply 2 here, the gate current start increasing in the left hand side. At one particular point, when the gate current is around 7 milliamps, that is IG1, immediately SCR turns on, voltage drop from 29.5 to 0 volts. This 29.5, because we've set initially 30, but slightly reduced when you keep increasing the gate current. 29.5 is the forward breakover voltage VB0 you have to note down, and then gate current is IG1 is 7 milliamps, and then a drop across the switch will be 0.8 volts, current will be 0.6 amps. All these things we note down here. The first reading we have taken. Then I want to increase the current up. Once the SCR is turned on, thereafter you don't want any gate signal. You don't want any gate signal. That's why SCR is called as a latching device. Latching, the specialty of the SCR is this. That is not the case with the transistor. Once the SCR is turned on, open the switch S2, remove the supply. Still SCR will be in the on state only. Current continues to flow here. 0.6 amps will be there. Even you remove the supply PS2, SCR will be in the on state only forever. Okay, that way the SCR is called a latching device. Now SCR is turned on. Then I want to increase you remove the gate signal thereafter, not required. Only first reading, till first reading we have the gate signal, thereafter remove the gate signal. The left hand side part is not at all required. SCR is turned on. Now the drop across the SCR is 0.8 volt and current is 0.6. I want to increase the current by cutting out the rheostat gradually. When you cut out the rheostat gradually, current will be increasing and voltage across the switch will be slightly increasing. Slightly, not 1, 2, 3, 4, 0.81, 0.82 like that. And current will be increasing from 0.6, 0.7, 0.8, 0.9 up to 1 we can go. And ensure that don't cut out the rheostat completely. When you cut out the rheostat completely, the load is shorted, the supply will be shorted because SCR is already shorted, it's already turned on. You're shorting the power supply 1, it will damage the power supply. So when you take a rheostat, we can cut out the rheostat from 0 to maximum 50%. Don't cut out henceforth. Till 50%, you can take some 7 to 8 readings. Okay, 0.6, 0.65, 0.7, 0.875 like that. Keep on increasing the current value. Note down, The probable values you might be getting, suppose if you see the tabular column, you'll be getting something 0.8, then 0.8 to 0.7, 0.9, then 0.8, then maybe 0.95, then you'll be getting current will be some 0.9 amps, then 1 almost, say 1 amps, like that. It will be keep increasing. Take some 7 to 8 readings. That is your readings with respect to PS1 30 volts, power supply 1 30 volts. So that's the first set. Next, what we do, conduct the same experiment by keeping PS1 20 volt. Instead of 30, you keep it 20 volt. Again, conduct the experiment the same way. What the same way? Initial conditions. Go to initial condition. PS1 should be 0 volt, PS2 should be 0 volt, current knobs of the both the power supply should be maximum. Next set PS1 20 volt, close the switch S1, same 20 volt will be available here, close the switch S2, gradually increase this from 0 towards 15 volt, 1, 2, 3 like that, current will be increasing. Now the current drawn will be little bit more than the previous case. It may at somewhere at 8 milliamps, say an example, SCR turns on because I kept the low voltage, right? The gate current will be a little bit more. Before it was 7 milliamps, so it's a little bit more. So it is a 8 milliamps. At 8 milliamps, what will happen? This is dropping from 19.5 volt to 0 volt. Why 19.5? 20 to 19.5 is a small voltage drop reduction because of the increase in the gate current. When you increase the gate current from 0 to 8 milliamps gradually, voltage will also fall gradually because of the leakage current flowing in the switcher. 19.5 volt. Then 19.5 volt, it switch over suddenly to 0 or a 0.8 volt, which means that SCR is turned on. So when the voltage drop across the switch falls from 19.5 volt to 0.8 volt immediately, that time SCR is turned on. So immediately current will also shoot up to 0.6 or 0.7. Now we have seen that 19.5 is the forward breakover voltage, VB0 2. Forward breakover voltage, IG2 is 8 milliamps. Okay, which means that when you keep reducing the forward breakover voltage, gate current will be maximum. It will keep increasing, their inverse. That's the meaning of this objective what I told you, to show that forward breakover voltage of the SCR decreases with increase in current, decreases with increase in gate current. So initially what I told VP0, I set it for 30 volt. Then it's slightly reduced to 29.5 volt in the period of increasing gate current. Suddenly reduces to 0.8 volt, where my gate current is IG is 7 milliamps. Right? The next case what I did, VB0 is set for 20 volt, where 20 volt is reduced to 19.5 volt when you increase the gate current gradually. It suddenly falls to 0.8 volt. That time gate current will be 8 milliamps, which means that when the VB0 is reduced from 29.5 to 19.5, gate current will increase from 7 to 8 milliamps. That's the meaning of this particular case. Same thing will be reflected in your graph also. So when you see the graph here, you can see IG1 and IG2, IG3 differences here is normally IG3 is more than IG2, more than IG1. Okay, lesser the VB0. So that you should analyze in the graph sheet, right? So IG3 in the gate current just idre forward break volt kadime saku, maybe 15 volt, it may be 20 volt, it may be 30 volt, like that. So this plot we are going to make it up. Maybe for 20 volt, as I told you, PS1 second set of reading what I do, second set of reading what I do is that PS1 is 20 volt, but it will go move or rush from 19.5 volt to 0.8 volt directly. The first reading SCR is turned on. The gate, the anode current flowing here is some current will be flowing. That time gate current will be 8 milliamps, which is more than the 7 milliamps available with respect to 30 volts. 0.8 volt, maybe current is some 0.6 like that. Then gradually increase the voltage here. Maybe some by cutting out the rheostat, we can increase the current. Current will increase, voltage will also increase. Maybe 0.8 to 1 volt, this 0.6 to 1.1 amps like that. But ensure that you should not cut out the rheostat completely. Don't cut out rheostat more than 50%. That is a very important thing. You should not do. Okay. So this is all about the first part of the experiment. Then once you write all of them, all the data, you can go for a plot. This is a plot. This is a plot. How you do the plot? This is a supposed to be 29.5 volt. So small leakage current flowing. Suddenly it switch over to 0.8 volt. 0.8 volt. Current will be some current, 0.6 of current is flowing. Thereafter current will be gradually increasing. My voltage will be very small increase, 0.8 to 1 volt, very small. This is the plot you have to show it in the first case. Second case, you set the power supply and the power loop as a 20 volt, not 30 volt. This is a 30 volt, this is a 20 volt. 20 volt means when you see the forward breaker voltage is 19.5. 19.5 suddenly goes to 0.8 volt. First reading, current will be 0.6 amps. Thereafter increase the current gradually up to 1 amps or 1.1 amps like that. But voltage will be small, increase in voltage will be there, 0.8 to 1 volt, not more than that. So we cannot take the in-between values. Please remember, all this value we cannot take. Only the switch over from the 30 to 0.8 volt directly. Okay, and respect to the current. So we can note down this point 30 volt or a 29.5 volt forward breaker voltage 29.5. So suddenly it goes to this particular point of 0.8 volt. Only these 2 points we get from the experiment. You need to join them in a very simple, high resolution manner, such a way that we get a smooth current waveform. Thereafter, these values, all this value we get in the experiment. 0.8 to 1 volt, the voltage will be increasing and the current will be gradually increasing to up to 1 or 1.2 amps. So this is the first part of the experiment. We again conduct for a 20 volts, where the forward breaker will be around 19.5 volt, switch over to 0.8 volt, all those things. The first part of the experiment. Then second part of the experiment is very important. What that experiment talks about is that there is something called latching current and holding current of the SCR. Very important. Latching current and holding current, both are anode currents only. So latching current IL, holding current IH. So what is it? Latching current and holding current means this is nothing but anode current. Now we require a certain value of current for SCR to turn on. If you want to turn on the SCR, the anode current should be minimum, should be latching current value. So we can see when the SCR is turned on, it is we are pointing is IL, latching current. The definition of latching current is minimum anode current required to maintain the turn on the SCR, and gate signal has been removed. Okay, that's the meaning. In the sense, once SCR is turned on, we don't want gate signal. Remove the gate signal. Left hand side, SCR is latched. So latching current means the current required to latch the SCR, turn on the SCR permanently. That is a latching current. Minimum anode current. Latching current is nothing but anode current. Don't think about latching and holding is nothing but it's a gate current. No, gate current is different. Latching current and holding current both are anode current only. It's a level of the anode current. How much the anode current is flowing. The definition of latching current is minimum anode current. Minimum anode current required to turn on the SCR, immediately gate signal has been removed. Okay, immediately gate signal has been removed. That is my latching current. Say latching current maybe some 25 milliamps is the latching current. This we cannot identify in this experiment setup because ammeter whatever I put is a 5 amps ammeter. I have here 5 amps ammeter. 5 amps ammeter will not show 25 milliamps and that's very small because latching current 25 milliamps. So it will move from 25 milliamps to suddenly to some 0.6 and all. We cannot identify where it's exactly turned on. So we need to change the ammeter from ammeter mode to milliamps mode. That we see the next part of the experiment. So you all of you note down. Latching current is the minimum anode current. Minimum anode current required to turn on the SCR, immediately gate signal has been removed. That's my latching current. Then Once SCR is latched, it never go to off state. If you want to turn off the SCR, your anode current should be less than latching current. But even if the anode current is 24 milliamps also, it won't turn off. Okay, there is some condition. Because my holding current is 15 milliamps as per standards. If the anode current is less than 25 milliamps, it won't turn off. If the anode current is less than 15 milliamps, you can see IH here. Then it will go to permanently off state. So you please note down holding current IH. Holding current IH definition is the minimum anode current. Is the minimum anode current required to. Is the minimum anode current required to maintain the thyristor in the on state. Required to maintain the thyristor in the on state, below which the SCR turns off. Required to maintain the thyristor in the on state, below which SCR turns off. Which means that if your anode current is more than latching current, SCR turns on. If your anode current is less than holding current, SCR turns off. In between it won't turn off. In between it won't turn off. Suppose my anode current is 25 milliamps, it will be on state. Reduce it to 24 milliamps, it won't go to off state. You go up to 16 milliamps, it won't go to off state. If you go 15 milliamps and below, it will go to off state. So these are some margins or current limitation values for the SCR. If somebody asks you what is latching and holding current of SCR, the latching current is current anode current above which SCR turns on. This is what you say layman language. Latching current is anode current above which SCR turns on. Holding current is anode current below which SCR turns on. Both are anode current only. Okay, please note down. This is a layman language. Otherwise, you have to tell the proper statement in the Viva. Okay, latching current is the anode current above which SCR turns on. Above which SCR turns on. That's a latching current. Point number 2. Holding current is the anode current below which SCR turns off. Below which SCR turns off. Okay.
So can we define holding current as
yeah, holding current is the
current at which SCR is on?
Okay, you want that statement? Okay. I told you latching current is the minimum anode current required to turn on the SCR. Immediately gate signal has been removed. I think you have noted on that latching current. Shall I repeat once again? Latching current. Actual statement is this. I am telling two definitions, one for the layman, one for the standards. When you go for standards, let us note on latching current, IL. All of you note on latching current, IL, is the minimum anode current. Minimum anode current required to turn on SCR. Required to turn on the SCR, comma, immediately gate signal has been removed. Immediately gate signal has been removed. Next, holding current IH. Holding current IH is a maximum anode current required to maintain the thyristor in on state. Maximum anode current required to maintain the thyristor in on state, comma, below which SCR goes to off state. SCR goes to off state. In layman language, IL is a latching current. Latching current is nothing but the anode current above which SCR turns on. Above which means 25 milliamps above. Okay, 25 milliamps and above. SCR turns on. Next, holding current is anode current, nothing but 15 milliamps, below which SCR turns off. So these are the statements. Now we are going to conduct the experiment for that. This is the separate circuit to determine latching and holding current. You can see here power supply 1, power supply 2, everything as it is. Power supply 1 is a 30 volt, power supply 2 is a 15 volt, switch 1 is 2 is there. There is no rheostat here. Instead we use a 10K pot because we are handling in terms of milliamps. Even my ammeter is 50 milliamps. Before we were using a 5 amps ammeter, now it's a 50 milliamps ammeter. 1 kilo ohm 2 watt, 5 ohm 10 watt, all of them are smaller values. We connect this. Even again, all these elements are available in the module. You have to rig up using a wires, that's all. Now you need to see how to find the latching current. So latching current and holding current will be given by this ammeter. Latching current, holding current will be given by this ammeter. No, the need not to worry about the gate current here. But here initial conditions are different. Initial conditions we made such a way that point number 1, initial condition point number 1, keep PS1 at 30 volts. PS1 at 30 volts, PS2 at 15 volt. PS2 at 15 volt. And pot in cut-in position. 10K pot. Pot means potential divider. 10K pot in cut-in position. Cut-in means entire resistance included. Okay, this is the initial conditions. Now you observe. This is 30 volt PS1, PS2 15 volt. We made the beginning only. Before PS2 was 0. From 0 we are increasing gradually, but here and also we keep it 15 volt directly. Close S1. Then voltmeter will show 30 volt directly because switch is not turned on. Then close S2. The moment you close S2 of 15 volt, SCR goes to on mode, but it's a temporary on, not permanent on. SCR goes to on mode. It will turn on. Once it's turned on, the voltage falls from 30 to 0.8 volt. Because we are doing instantaneously. Close S1, voltmeter shows 30 volt. Close S2, then the voltmeter shows 0.8 volt, and here some maybe some 2 milliamps of current will flow. Okay. Next, what you should do, open switch S2. When you open switch S2, we expect that SCR is latched. It's already turned on. It won't go to off state, but that becomes false. That becomes false. The moment you open S2, again voltage will go back to 30 volt. From 0.8 to 30 volt, it goes to off state suddenly. Before experiment, we were increasing the gate current up to 7 milliamps. Then the SCR is turned on permanently. Remove the gate signal. Still SCR will be on, but here it's not so. The moment you open, SCR goes back from 0.8 to 30 volt. It will go from on state to off state back. That is, we say, quasi turning on. Quasi means false. It's not permanently turned on. It's a quasi turn on. That's a temporary turn on. It's not a permanent turn on. Then what you should do? The anode current is 22 milliamps. That's the problem. I told you the minimum current equal to turn on thyristor permanent is latching current. Latching current will be up to 25 milliamps. Above 25 milliamps only SCR will be in on state. Then what you should do? Again close. This will be S2 will be always, S1 will be always on. The moment you open the S2, it's gone from 0.8 to 30 volt back again. Again close S2 and increase the anode current by cutting out the rheostat. Let us say you set this value, say 10 milliamps. 10 milliamps, okay? 10 milliamps. Then again open switch S2. When you open the switch S2, again the voltage across the switch moves from 0.8 volt to 30 volt. Which means that again this is not permanently turned on. It's not permanently turned on. When you close the switch, voltage grows from 30 to 0.8. When you open the switch, voltage goes back from 0.8 to 30 volt. It's a temporary turn on. Next, what you should do? Let the switch will be closed only. Increase the anode current from 10 to 20 milliamps, say 20 milliamps, but it's still not reach 25 milliamps. Set to 20 milliamps. Open the switch. When you open the switch, suddenly voltage falls from 0.8 back to 30 volt. It's not a permanently turned on. Again close the switch S2, it moves from 30 to 0.8. Again open the switch, it goes from back from 0.8 to 30 volt. It's not permanently turned on. So to increase the anode current, close the switch S2, increase this current from 20 to 25 milliamps, say 25 milliamps. Since S2 is already closed, here the voltage is 0.8 volt. Now we open the switch S2, it will remain to be 0.8 only. It won't go from 0.8 to 30 volt, which means that SCR is turned on permanently. That respective current of anode current, we say latching current of the anode current. Anode current is nothing but latching current that time, which means that minimum 25 milliamps of current should flow in my power loop. Then only SCR will be permanently turned on. Otherwise, it won't turn on. It will go temporary mode, temporarily turn on because I'm giving a huge voltage across the gate to cathode of 15 volt. It temporarily goes to on state. Okay, because I kept PS2 15 volt constantly from the beginning of the experiment. I'm not varying that. So this is the way of identifying the latching current. Latching current is a minimum iron current required to maintain the required to turn on the SCR, below which it will, above which only it will turn on. Immediately gate signal has been removed. That's what we did here. Now I'll tell you the same experiment steps once again. Now down, set PS1 30 volt, PS2 15 volt, close S1 so that here we get a 30 volt because switch is in off state, close S2, switch will go from 30 to 0.8 volt in the voltmeter. It turned on. Okay, because switch is in on state, S2 on state. When you turn off the switch S2, it again go back to 30 volt, which means that SCR is temporarily turned on. Again on the switch S2, it moves from 30 volt to 0.8 back in. It will turn on 0.8. Again open the switch off the switch, it will go back from 0.8 to 30 because it's not permanently turned on. What we expect, SCR should be latched. Once it's latched, gate signal is not required. That's why I'm removing the gate signal. Open the S2 means removing the gate signal. When you remove the gate signal, it's going to off state. It's not permanently turned on. Then close the switch S2. Increase this anode current by cutting out this pot, so that initially it may be some 2 milliamps. You increase it to 10 milliamps by cutting out this pot, 10 milliamps. Then open the switch again. When you open the switch again switch over from 0.8 to 30 volt. It is in off state. Again the close switch S2. It will come back to 0.8 volt. Then gradually increase this anode current from 10 milliamps to 20 milliamps by cutting out the pot here. Cutting out the pot. Then open the switch S2. Then it again go to off state from 0.8 to 30 volt off state because my anode current is not more than reaching the 25 milliamps, which is the latching current level. The next what you do, you set it to maybe 25 or 28 volt like that, 25 volt maybe. Okay, increasing the anode current to 25 milliamps. Then again open the switch. The voltage will remain to be 0.8 only. It won't go to off state, which means that the respective anode current is my latching current. Latching current, note down latching current and tablet it. Tablet here, latching current is maybe 25 milliamps here. So we take only two values here, nothing else. Second part of the experiment. I got 25 milliamps latching current. Now I want to find only holding current. Since it's latched, don't bother about the gate signal henceforth. It's permanently latched. Then S2 will be off state only forever. It's in off state only. We don't want any gate signal because permanently latched by my latching current is 25 milliamps. Permanently latched. Gate signal thereafter is not required. So that I got by cutting out the pot. Now to find the holding current, what you should do? Now 25 milliamps of current is flowing. You have to cut in back the rheostat by using a pot such a way that when you increase the resistance, cutting in means increase the resistance, current will reduce. Now what will happen here? 25 milliamps is there. Then it will go to maybe 19 milliamps. It won't go to off state. Voltage will still 0.8 only. Okay. Some you go to 18 milliamps. Voltage is 0.8 only. It's not. We are not finding the holding current. The moment you go 15 milliamps, okay, nearby, suddenly this voltage comes back to 30 volt. Comes back to 30 volt, which means that SCR gone to off state. It's jumped from 15 milliamps to 0 milliamps, which means that this is my holding current. Holding current is the maximum anode current, 15 milliamps, below which it goes to off state. 15 milliamps is the maximum anode current it can flow, below which it go to off state. So I tell you once again how to find the holding current is that my SCR is already turned on. My anode current is 25 milliamps from the previous part. Open the S2, don't worry about this supply. Now 25 milliamps of current is flowing in the circuit. Now I was going from cut-in to cut-out. Now I go back from cut-out to cut-in, cut-out to cut-in. So that I increase the resistance. So the current in the power loop will be reduced. You please note down. I cut in, going to cut in towards cutting means I am increase the resistance so that current, anode current will be reduced gradually. So keep on cutting in. So it will go to 25 milliamps. Here drop is only 0.8 volt. 25 milliamps no problem. 24 no problem. 20 no problem. 15 you go reach nearby 15. Suddenly current goes to 0. The voltage comes back to 30 volt because SR is turned on, turned off. It's a turned off because 30 volt is available at the switch. The respective current we say holding current. You can see in the plot here. Yeah, I'll show you. So this is my latching current point 25 milliamps. Thereafter the current is increasing. Okay. This is my holding current 15 milliamps, below which it goes to off state. Off state means it comes back to again 30 volt again. On state means the voltage drop across the switch will be 1 volt, less than 1 volt. Off state means the voltage will be 30 volt, 30 volt. So what will happen? The voltage will be come back to 30 volt here. That's my holding current is small. You can see holding current will be lesser than the latching current. As per theoretical aspects, as per theory, what they say is the latching current will be 3 times of the holding current, or 2 to 3 times you can say. 2 to 3 times the holding current, latching current. So latching current will be higher, holding current will be always smaller. Or holding current is normally as per theory 1/3 of the latching current or half of the latching current. Okay, it will come in between 2 and 3 normally, not exactly 2 or exactly 3, it will come in between them. So this is the readings, we take it here and dump it here. So for what and all we got it here is that holding current we got to know is at 15 milliamps, latching current is 25 milliamps, gate current at the gate current of IG1 of 7 milliamps, the breakover is 29.5, the gate current of 8 milliamps, the breakdown voltage is maybe around 19.5 volts. These things we record from the graph. And also one more thing interesting is we come to know what is the on-state resistance of the switch. On-state resistance is turned on. What's the resistance offered by the switcher? So when you say on-state resistance from this graph, you put a small slope there. Put a small slope. You can see the slope here. Delta VAK versus delta IA. This is a delta VAK. That's VAK1 minus VAK2. IA1 minus IA2 is a delta IA. Take the ratio. Voltage by current. So on-state resistance of the SCR is delta VAK by delta IA. That is your R on. On-state resistance of the switch, that's R on. So that also you note down, you'll be getting very small value. So 1 ohm, 2 ohm, whatever you get, you can note down here. So this is about the experiment number 1. Any doubts you have, you please let me know. Do you have any doubts here? So you keep it in mind that latching current will be more than the holding current. Latching current is referred to turn on condition of the switch. Holding current refers to turn off condition of the switch. So when you conduct the experiment, rig up and conduct the experiment and note on the readings, you get the clarity how to do that. Do you have any doubts? Students, are you there? Disha? Dimple?
Yes, sir. Understood.
Okay. Yes, fine. Anyway, you go through the procedure given in the manual which you are going to circulate today only, and definitely once you come to the lab, we'll explain you once again also if required, but you should know the procedure. We'll ask you some Viva question there itself. What is latching current? What is volting current? What is forward breakover voltage? What is reverse breakover voltage? All those things should be aware of. Okay. That's about this experiment. Now we go to the second experiment, static characteristics of the MOSFET and the IGBT. Now here what I do, only if you understood MOSFET, the experiment conduction, IGBT will be similar, circuit will be same. I replace MOSFET with the IGBT, that's all. The symbol for IGBT will be something like this. This is my IGBT. IGBT. In IGBT, the power terminal is collector, common terminal is emitter, control terminal is gate. So IGBT is a combination of BJT and MOSFET. Why they combined is that there are two advantages. One advantage, BJT offers low on-state resistance. That's why you can see on the right hand side, collector emitter is the terminal of the BJT. And MOSFET offers high input impedance. It will draw very small current at the gate terminal. High input impedance. So high input impedance is always good for us because we draw very small current at the control terminal, and low on-state resistance on the power terminals is very important because there will be less losses in the switch, less voltage drop in the switch, and less power loss in the switch. The BJT plus MOSFET put together is your IGBT. Okay, but I'm going to discuss only MOSFET conduction because IGBT we do the same thing. I'm not going to discuss the same thing again and again. Now we are going to learn the static characteristics of the MOSFET alone. Okay. So first of all, you should know what is MOSFET. MOSFET stands for metal oxide semiconductor field effect transistor. It's a voltage control device. Voltage control device means you give the voltage, proper voltage to turn on, VGS to turn on. But when you talk about the SCR is a current control device. There we talk about the gate current, IG1, IG2, IG3. Here we talk about the VGS1, VGS2 like that because it's a voltage control device. Between gate and source, we have a huge capacitance effect. It's a voltage control device. And your IGBT is also voltage control device, but SCR and BJT are the current control devices. There we talk about gate current, base current like that. Okay. So you note down BJT, SCR, they are current control devices. MOSFET and IGBT, they are voltage control devices. These are the Viva questions, voltage control devices. Now let us go to the experiment. Here for MOSFET, we do for a two characteristics. One you call transfer characteristics. Transfer characteristics we are going to plot. Transfer characteristics we are going to plot. One more we are going to plot output characteristics. We are going to plot two things. One is transfer characteristics, another one is the output characteristics. Okay. From the transfer characteristics, we are going to find the transconductance GM of the MOSFET. From the output characteristics, we are going to find the output resistance of the MOSFET, R0 or RDS. So RDS should be very, very minimum. Okay, that is very important. Now let us see what are the parts of the circuit conduction, experiment conduction. We have a MOSFET here. Gate, G stands for the gate. Gate is the control terminal. D stands for the drain. Drain is the power terminal. S stands for the source. Source is the common terminal. Similar to your thyristor, we say anode is your power terminal like a drain. Cathode is the common terminal like a source. Gate is the control terminal, is common for both SCR and the MOSFET. And we can see this small resistance across the MOSFET between G and S. 1 kilo ohm resistor is there because there is a capacitance effect between the gate and the source. Once the MOSFET is turned on and supply is removed, what are the energy stored in the capacitance has to be dissipated, has to be discharged. So for that we put one resistor here for discharge process to happen. So from gate to source, the capacitance effect, it will discharge through these resistors so that energy in the MOSFET will be nullified. So this is a very sensitive device, MOSFET. When you touch bare-handed, it will burn because our body has got a huge energy, okay, electrostatic energy. Once you touch the MOSFET directly, the power flow from your body through your hand, finger, to the MOSFET, it will burn. Okay, it will lose all its power. Okay, it will damage within no time. That's why you should handle very carefully. You should not touch the drain or source of the MOSFET, the gate or source of the MOSFET by barehanded directly. If you want to conduct this experiment, you have to touch your body to some metallic part like a metal knob or a door like that, or an earth point. Then you have to handle this circuit. Okay. Now, first of all, understand what is transfer characteristics as far as plot is concerned. When you say transfer characteristics is a plot of output current ID versus input voltage VGS. So my y-axis is output current, and x-axis is input voltage. So since the current and voltage, output current to input voltage, that's what's called transfer output to input. That is the transfer characteristics. Okay, the very meaning of transfer characteristics means it's a plot of output current versus input voltage, not output current output voltage or input current input voltage. When you take input current input voltage, we say input characteristics. Output current versus output voltage, we say output characteristics. But to take one parameter output, one parameter input, we say transfer characteristics. It's a plot of output current versus input voltage. That's the transfer characteristics one we do. Second one is as usual output characteristics. When you say output characteristics, it's a plot of your output voltage ID versus, there's a mistake here and output voltage, output current ID versus output voltage VDS. So output voltage, output current, that's basically output characteristics. Okay, so let us see how to conduct this experiment. Let us see all the initial conditions. Initially, what you should do, you can see what are the elements available here. We have a switch here, MOSFET. Load is same 25 ohms, 6 amps rheostat. Supply is 30 volts. So this is the supply, power supply. This is the load, and this is the switch. These are the three elements coming in the power loop. In the control loop, we have given the 15 volt across the gate and source directly. There is no any controlling resistor. We have 15 volt, 500 milliamps, but we don't give it at a time. We gradually increase the voltage from 15 volts onwards. Now, this is the power loop and this is the control loop. Okay, when you increasing the gate voltage gradually, maybe as 1 volt, 2 volt, 3 volt, somewhere at 3.3 or 3.5 volt, somewhere at that particular point, a small drain current flows. The drain current will be some 0.01 amps. Then we can conclude that at that point of 3.5 volt, the drain current is start flowing. That is the first reading we are going to take in the tabular column. What you have done, you observe here. VDS I kept 30 volt, output side I kept 30 volts. I keep on increasing the gate voltage. At particular point, maybe 3.5 volt, the drain current is 0.01. The respective threshold voltage, what you call 3.5 volt only. This is my threshold voltage, VGS threshold. VGS threshold, we say cut-in voltage of the diode, like same thing. VGS threshold is the voltage beyond which current will be start increasing. Okay, then once I got the reading here 3.5 volt and 0.01 amps, thereafter you increase further your PS1, increase further PS from 3.5 to maybe 3.6, 4, 4.5, 5 like that. Up to 15 volt you can go, no problem. You can take some 5 to 8 readings. That is a plot of VGS versus ID, keeping your VDS constant of 30 volt. 30 volt. Okay, we take tablet all the values here. 3.5, 3.6, 4, 4.5, 5, 10, 15 like that. Current will also increase from 0.01 up to 1 amps. Okay, or to 1 amps. That is the first set of reading we take. So it's a plot of your output current ID versus input voltage VGS, keeping the VDS constant. Next term. For second set your VD, the PS2 to 25 volt or 20 volt, no problem, 25 volt. Again, gradually increase this PS1 from 0 volt towards 15 volt. Again, if you observe somewhere at 3.5 or 3.51 volt like that, again the small current will flowing here. Till then no current will flow. 3.51 onwards, some small current start flowing. That the moment some small current of 0.01 of current flows, you would either take the first reading. So first reading is my VGS is 3.51, which is nothing but VGS threshold, and the drain current is 0.01. For the VDD is we say it's a VDD, not VDS. VDD is that 25 volt. Our PS2 is 25 volt. Why is not VDS ಅಂತ ಹೇಳಿದ್ರೆ, this is VDS actually. VDS is the exact voltage drop across your drain and source. VDD is a PS2 voltage. VDD is 25, but VDS need not be 25. It can be some other value also, because there's a drop across your load. Drop across the load. Gradually increase VGS, this particular source, and node on maybe 3.5, 4, 4.5 up to 15 volt you vary, and node on maybe 1.1 amps, 1.2 of current is flowing, and plot it. They are directly proportional. So this is a plot we are going to get. You can see this is my 3.5 volt, 3.5 volt. Thereafter increase the voltage with VGS, then gradually current will increase. Somewhere it will go to 14 or 15 volt. You can tabulate it, no down. Then take the slope here. When you take the slope here, what you call transconductance GM. So is equal to Y by X. Y by X is nothing but Y is delta ID, the change in the drain current. Delta VGS is the change in the input voltage. So this will be getting some value, maybe 2 mhos or 2.4 mhos like that. Some value will get 1 ohm to 2.5 mhos, till mhos will be getting. This is a conductance, so it's a mhos, not ohms. Okay, this is a transconductance of the switch. These are things we are going to get from the first part of the experiment, what you call transfer characteristics of the MOSFET. Then I'll tell you the same thing once again. All of you observe. That's the transfer characteristics. What you should do. Procedure point number 1. Point number what we should do. Set PS2 to 30 volt. Okay. PS2 to 30 volt. So same 30 volt will be available here also, because switch is open. Then gradually increase your PS2 from 0 volts, not from 15 volt, from 0 volt. Gradually increase. When the VGS approaches somewhere at 3.5 volt, then the drain current, a small current will be flowing. Till then there is no current, small drain current will be flowing. This respective gate to source voltage is called as a VGS threshold voltage, or a cut-in voltage, beyond which the switch will be conducting. Once the switch start conducting, the respective voltage is a threshold voltage. So thereafter it's a VGS will be maybe 4 or 5, you can go further. The current will also increase further. You tabulate all these things for the constant VDD of 30 volt. Constant VDD of 30 volt. Okay, this is not VDS actually. There's a small mistake, because VDD, VDS very. It's VDD. Nothing but power supply, right hand side power supply. The next, again what you do, set your VDD or a PS2 to 25 volts. You can keep 20 also, no problem. You can still conduct, maybe 25 volt. Gradually increase this from the 0 volts onwards. Again at somewhere at 3.5 or 5.2 like that, not exactly the previous value, 3.5, 5.2. Small drain current flows, that current is 0.01 amps. So this is my VGS threshold, which I have to note on the first reading. 3.5 to 0.01 are the values. I have to write it here. So this may be 3.5 to this is a 0.01 first reading, because this is the minimum current at which the switch is conducting. This is my VGS threshold. Same thing I can copy here also, 3.5 to 3.5. If I got 3.5 here, 0.01, this also 3.5. So these two are same. First reading is a VGS threshold value, I can note down. Thereafter, gradually you have to increase the gate source voltage. Gradually increase the gate source voltage such a way that your drain current will start increasing, and you can note down your ID VGS. Don't worry about VDS now. IG VDS. So those things you have to note down and tabulate it and plot it. From the plot, you are going to identify two things. One is threshold voltage, which you know already from the tabular column, from where the current start flowing. And another is you take a slope here. Take your slope is Y by X, that is delta ID by delta VGS. So that is your GM, transconductance. Transconductance delta ID by delta VGS. Okay. So in mhos, you may be getting 1 mho or 2 mho or 2.5 mhos over here. Okay. Now we go to the output characteristics, which is very, very important. We have some typical procedure here. You please observe carefully here. Observe carefully here. Output characteristics. Can you tell me what is output characteristics here? Plot of what and what? Output characteristics, the plot of what and what this stands for. What is output characteristics? Yes, tell me, Gurana. It's a plot of what versus what. You can see the plot there. Gurana? Gurana is there? Gurana is there?
He is there, but not answering, I guess.
Not answering. Yenaithu Gurana? Last class, last semester, Gurana first answer madam. Can you unmute Gurana? Adisha? You can unmute Adisha. Apurva?
Yes, sir.
The question is, what is output characteristics of the MOSFET? What is X versus Y? What is the stands for? You can see the plot there itself. What is the output characteristics of the MOSFET? What is the Y-axis? What is your X-axis?
Y-axis is I0 and ID, and X-axis is VDS.
Output current, that is ID is output current versus VDS. VDS, that is your output voltage. So output current versus output voltage, that's why we call it as output characteristics. Correct? Both are output parameters. Input parameter here is VGS and IG are the input parameters. Output parameters are ID and VDS. Okay. So when you take one parameter output side, one parameter input side, that we say transfer characteristics, maybe plot of ID versus VGS, the first thing what you have done, first case what you have done in this experiment. Now we see the output characteristics. So you should listen to this steps carefully, and then you are going to take only 6 readings here, exactly 6 readings. I'll tell you how to do the 6 readings. You'll be taking only 6 readings here, no doubt about it. But let's see how to take those readings. In the output characteristics, first and foremost thing is set your VGS little bit more than the VGS threshold. So by this time I came to know that VGS threshold is 3.5 volt in the previous experiment. So maybe keeping some 3.8 or 3.9 volt, little bit more than the VGS threshold, beginning only. Keep your VGS little bit more than the VGS threshold. What you call VGS threshold is 3.5. We came to know in the previous case. Set it to 3.9 volt. Okay. Why we do this is, if you observe in this experiment, in case you make the PS switch 30 volt, same 30 volt is available here. As I told you, this is VDD, not VDS. This is a VDS. VDD is 30 volts fixed, but VDS is need not be 30 volt. It may reduce also. Then actually this is VGG in fact, but in this case there is no any resistance there. VGG and VGS both are one and the same. Let us say VGS only, the supply voltage. While increasing VGS gradually from 0 to 3.5, no current is flowing, so that my VDS is 30 volt only. VDS is 30 volt only, but VDD is also 30 volt. The moment you increase the VGS more than VGS threshold, that is maybe 3.9 volt, which is more than 3.5 volt, this VDS falls to 50 to 60% of the VDD. If I say 60%, it falls to 18 volts. VD is 30, no doubt, but VDS falls to 18 volt because I am increasing the current. The VDS, the drop occurs, the switch is reducing, so it's a 18 volt. So this is the initial condition. Initial condition says that point number 1, set VGS on the left hand side more than VGS threshold such that this VDS falls to 50 to 60% of the VDD, that is around 18 volt. We'll come to 18 or 20 volt, no problem. Stop with that. Thereafter, don't touch this VGS. It's a constant. 3.9 is constant. Okay, so 3.9 is constant. So that you have to note down. So VGS is 3.9 volt here. So I kept VGS 3.9 volt, which is more than VGS threshold. Then respect to VDS, I have got somewhere at 18 volt, something like that. Current will be some current is flowing there, maybe 0.6 points, and some current is flowing there. Okay. Then once I achieve that, of course, I'm not going to take the reading. That's the initial condition, what I'm telling. Now we came to know that VGS is 3.9 volt. Let me note on this. Just a minute. So this is 30 volt. I set VGS to 3.9 volt. Thereafter, you don't do any reading such a way that we inspect that VDS fall from 30 to 18 volt, which is 60% of the VDD. This is the initial condition. Then I take 3 readings here. How I take 3 readings means set your VDD to 10 volt, reduce this to 10 volt, and note down your drain current, and increase VDD to 20 volt, right hand side, note down the drain current. Further increase VDD to 30 volt, note down the drain current. 3 readings over. Once the voltage is maximum 30 volt VDD, next 3 readings I'll take reading number 4, 5 and 6 by cutting out the rheostat gradually. Cut out the rheostat a little bit, take down your VDD versus ID. Again further cut out, take VDD versus ID. Further final cut out, take VDD versus ID, stop reading. So these are the 6 readings I take in the output characteristics, provided my VGS is input side VGS is 3.9 volt, which is constant forever. That is why when you see the graph here, table, VGS is a constant, VDS and ID I'm noting down by setting my different values of VDD 10, 20, 30, I take VDS readings, ID reading, and again cutting out the rheostat, I take another 3 readings. So I tell you once again, the 2 important points you please note down. The first point is set VGS more than VGS threshold, means maybe 3.9 volt. Okay, by operating the voltage setting knob of the PS1, so that VDS, this VDS reduces to 50 to 60% of the set value of the PS2. Here is 30 volt already fixed. So VDS will be reduced to 60% of the VDD or a PS2. That's the initial condition you have to do here in the point 1. Point 2, what you should do, let it be 3.9 volt VGS as it is, don't touch the PS1 forever. Now this VDD, you suddenly reduce it to 10 volt. Take one reading, 20 volt, take second reading, 30 volt, take third reading. What are the readings? This is actually VDD, not VDS. VDS will be falling actually. It will be falling to 18 to 6, 5, 4, 3 like that, and ID. These 2 readings will be taking from this voltmeter and this ammeter, VDS and ID. 3 readings will be taking. Then next 3 readings will be taking by cutting out the rheostat. So cut out the rheostat and take the readings of the VDS and ID. So VDD is already 30. We cannot increase more than that. For remaining cases, your VDD is 30 only. 30 only. Only VDS will be seeing the changes there. So for that, what I suggest here is that you put one more column here. You note this table, all of you, as a VDD. VDD, 10 volt, take the reading, 20 volt, 30 volt. Thereafter 30 volts only, another 3 readings. But in the last 3 readings, we take the reading by cutting out the rheostat. So this zone, rheostat, cut in. These 3 reading, you have to cut out gradually. Rheostat, cut out the rheostat. VGS is 3.9 fixed. Okay, this is the one set of reading we take in here. Oh, somebody can explain this. If you understood this, everything is done actually. Somebody can explain what are the steps I told you here? Apurva, what the first step I told you? We can read this. If you have a doubt, you can read this what I am showing here. You please tell me, Apurva, read this statement.
Yes, sir. First, PS operating PS1, we make sure that VDS reduces to at least 50 to 60% of the set value.
So set value is 30 volt here, and here you increase this gradually such that your VGS is more than VGS threshold, that is a 3.5 in the ಜಾಸ್ತಿ ಇಡಬೇಕು, more than VGS threshold, such that VDS falls to 60% of the VDD. Correct? There's a first initial condition you have to do. Then what should I do to take the readings?
Then PS2 is made 0 and
Zero.
VDS and ID are taken.
Yes, PS2 is made 0, and then what are the values we made for PS2? First reading 10 volt, second reading 20 volt, third reading 30 volt, maximum, that's all, over. Only 3 readings we take it here. Next, what should I do? Next 3 set of reading, what should I do?
Increase collector current.
Increasing collector drain current by cutting out the rheostat. Correct? Cutting out the rheostat, 3 readings, don't go more than 50%. Cut out the rheostat and take another 3 readings. That ends your output characteristics of the MOSFET. Then what you should do, tabulate them, and this is a plot. You can see the plot here, plot of output voltage is output current. It will increase gradually in saturation mode. Thereafter drain current won't increase. Okay, drain current won't increase, and you can see here there are even for, we can go for VGS 3.8 volt, VGS 3.5 volt, like that we can go for various settings. Take the slope here. So, and then you can also identify here output resistance from this. Output resistance is R0 is equal to output voltage delta VDS by output current delta ID. Output voltage by output current by output resistance. You have to note down the R0. R0 will be varying from somewhere at 200 to 500 ohms also, practically 200 ohms to 500 ohms. But we expect 1 ohm or 2 ohm. Why we are getting very high values? Because we are going to apply only 30 volts for the VDS. This is only 30 volt. You are supposed to apply the 600 volt for this MOSFET, 500 volt for this MOSFET. We are using the MOSFET called IRF 830, whose forward breakover voltage is 500 volt, or the forward blocking voltage is 500. If you give 500 volt DC and conduct, then the resistance will be 1 ohm or 2 ohm. But we are not doing that. We are just giving a small voltage just for safety purpose. Then the resistance will be 200 ohm to 5 ohms we will get. That's no problem. You can note down that value. So that's about the output characteristics. So we should understand that for a MOSFET, VGS threshold is 3.5 volts, somewhere at 3.5 to 3.9 volt VGS threshold. But for IGBT, the experiment remains same, no changes. For IGBT, the VGS threshold is around 5 volts. Okay, 4.5 to 5 volts, around 5 volts. 5 volts onwards only, the collector current start flowing in the IGBT. Like in the MOSFET, if it's more than 3.5, then the drain current is 0.01 amps. Thereafter, it's increasing. Same way here also, if the gate voltage is more than 5 or 5.5 volt, then only current will start increasing from 0.01 amps. So this is my threshold voltage for the IGBT. Rest of the part, everything is same. So I'll tell you how to conduct the transfer characteristics for the IGBT. Just observe. Set PS1 30 volt. Same 30 volt will be available across the VCE. Then gradually increase PS1 so that somewhere at 5 or 5.5 volts, the small current 0.01 of current is flowing in the power load. So that's my first reading. 5.5 is the threshold voltage. Respective collector current is 0.01. Further increase this up to 15 volt. Note down VGE input voltage versus output current IC. Tabulate it and plot it. It's a plot of IC versus VCE. This is my VGE threshold, and thereafter the current will be start increasing. Take the slope, take the ratio of delta IC by delta VCE. That's the transconductance of the IGBT. Then Do the experiment, repeat the experiment for your VCE 30 volt as well as 20 volt. Then output characteristics, same steps I'll tell you. Set your VGE little bit more than VGE threshold, that is more than 5.5 volt. If you keep this 5.5 volt little bit more than that, then the small current start flowing 0.01 amps. Next, what you do, take your PS2, make it 0, set for a 10 volt, take one reading of IC and VCE, set 20 volt, note down IC VCE, set 30 volt, note down IC VCE. So this is with respect to rheostat in cut-in position. Then put the rheostat or increase the rheostat, or otherwise you say cut out the rheostat gradually to increase the collector current. Then your VDs, your PS2s remain same. We are not touching PS2. Increase the collector current. Note down another 3 readings. That is VC versus IC. And tabulate it, plot it. You will get the curve like this. You can see that current will be remaining constant. It won't increase drastically. After one particular point, current will be constant. That point we say pinch off voltage. Pinch off voltage is the voltage you can see here at which the collector current goes to saturation mode. Saturation mode, it won't increase further. That we say pinch off voltage point. And take the slope, you will get a output resistance delta V by delta I. The delta VC by delta IC is the change in collector voltage with changing the collector current, that is my output resistance R0, and tabulate it. So these are the 4 different values we are going to note down. GM R0 from the MOSFET and GM R0 from the your IGBT. Okay, both are one and the same. You should remember that VGS for the MOSFET is 3.5 and VGE for the IGBT is around 5 to 5.5 volts. Why I'm telling the range is, if you take 2 MOSFETs of the same manufacturer number, IR of 830, no 2 MOSFETs will give the same features or the values. No 2 MOS transistor will give the same alpha, same beta. It will be small variation will be there. Same thing here also. Okay, that is why I told you the band is 3.5 to 3.8 for the VGS threshold for the MOSFET, 5 to 5.5 volt VGE threshold for your IGBT. And IGBT is equal to MOSFET plus your BJT. Okay, MOSFET plus BJT is nothing but IGBT. It's a combination of those two. Of course, IGBT is suitable for the high power applications. MOSFET is for the middle and low power applications. Any doubts you have here? Let me take the attendance before leaving the class. Then you can leave exactly 1 p.m. I stopped. If you want, I can share this PPT also. Maybe it will be useful for you. Right. Let me go to the, where is it? P lab session. P lab. Let me share the manual, everything right now. Yeah. P lab manual. Champa ma'am.
Yes, sir.
Share ಮಾಡೋಣ ಮ್ಯಾಮ್ ಇದು ಮ್ಯಾನ್ಯುಲ್ ಅವ್ರಿಗೆ.
ಸರ್ ಅದರಲ್ಲಿ
ರೀಸೆಂಟ್ ಏನಾದರೂ ಇದೆಯಾ ನಮ್ಮ ಹತ್ರ?
ಇಲ್ಲ, ಸ್ವಲ್ಪ ಮಾಡಿಫಿಕೇಶನ್ಸ್ ಮಾಡ್ತೀನಿ ಸರ್. ಇವಾಗ ಒಂದ್ ಸ್ವಲ್ಪ ಕರೆಕ್ಷನ್ಸ್ ಇದೆ ಅದ್ರಿಂದ. ಅದ್ ನೀವ್ ಹೇಳಿದ್ರಲ್ಲ ಅದೆಲ್ಲ ಟ್ಯಾಬ್ಲೋ ಕಾಲಮ್ ಅದನ್ನ ನಾನೇ ಹಾಕ್ಬಿಟ್ಟು ಕೊಟ್ಬಿಡ್ತೀನಿ. ಮತ್ತೆ ಅವ್ರಿಗೆ ಕನ್ಫ್ಯೂಷನ್ ಬೇಡ. ಅಸೆಸ್ ಬೇಕು ಅಂದ್ರೆ ಫಸ್ಟ್ 6 ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್ ಕರೆಕ್ಟ್ ಆಗಿ ಮಾಡ್ಬಿಟ್ಟು ಕಳಿಸ್ತೀನಿ ಸರ್. ಅದಾದ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ 6 ನೋಡೋಣ. ಫಸ್ಟ್ ಸೈಕಲ್ ಆದ್ರೂ ಕಳಿಸ್ತೀನಿ ಅಟ್ಲೀಸ್ಟ್.
ಇವ್ರಿಗೆ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡುವಾಗಲೇ ನಮಗೆ ಮ್ಯಾನ್ಯುಯಲ್ ಎರರ್ಸ್ ಗೊತ್ತಾಗ್ತಾ ಇರುತ್ತೆ. ಬಟ್ ನೀವು ಅದೆಲ್ಲ ಚೇಂಜ್ ಮಾಡ್ಬಿಟ್ಟು ಕಳಿಸಿದ್ರೆ ಅವ್ರಿಗೆ ಹೆಲ್ಪ್ ಆಗುತ್ತಲ್ಲ.
ಮಾಡ್ತೀನಿ ಅದನ್ನ ಚೇಂಜ್ ಮಾಡಿ ನಾನು ಫಸ್ಟ್ 6 ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್ ಮಾತ್ರ ಕಳಿಸ್ತೀನಿ ಸರ್ ಅವರಿಗೆ. Probably by today or by tomorrow I'll send them.
That is good then. So ಹಾಗಾದ್ರೆ ಈಗ
modifications ಮಾಡ್ತೀನಿ.
ಸರಿ ಹಾಗೆ ಮಾಡೋಣ. Okay then. I think Champa ma'am will share you the manual with the corrections what we have identified now. With the corrections, all the corrections will be rectified and then we'll send to you. Now let me take the attendance before you people leaving the hall. Let me stop recording.